In the last lecture, we talked about atoms. There's a lot of different kinds of atoms that we know about. They make up all of chemistry, and then they string together to make up all of biology. We have a periodic table of the elements to explain how the different atoms fit together into patterns, but the remarkable fact is that every single atom is just a different rearrangement of three different elementary particles: the electron, the proton, and the neutron, with the electron spinning around and the proton and the neutron in the nucleus. And then we know that the proton and neutron are both made of smaller particles called quarks, but you only need two kinds of quarks to make protons and neutrons, the up quark and the down quark. So you have three fermions that make up everything that you've ever seen in the universe: the up quark, the down quark, and the electron. They're held together by two different kinds of bosons. There's the photon that carries the electromagnetic force, holding the electron to the atomic nucleus, and there's the gluons. The gluons keep the quarks together inside the proton and the neutron. So that's five kinds of particle that describe everything that you have ever seen in the universe. However, the theme of our lectures is that all of that stuff, all of that ordinary matter, is only 5% of the universe. Who really cares about the 5%? We are interested in the 95% that is the dark matter and the dark energy. So the dark matter and the dark energy, we will tell you later, are not made of electrons, protons, and neutrons, not made of any arrangement of up or down quarks, or electrons for that matter. We need to find some new particle to make up the dark matter. So what we're going to do in this lecture is go through all of the known kinds of particles. It turns out that there are more particles that exist, that we know about in nature, that we've discovered through doing experiments, than just the two quarks and the one electron. They fit together in nice patterns, and together all of these particles and their patterns are called the Standard Model of particle physics. So in this lecture, we're going to go through all of the particles of the Standard Model, a total of 12 different kinds of fermion and 5 different kinds of boson. And we will systematically point out why they can't be the dark matter. No particle, of course, can be the dark energy, so we're stuck with that as a mystery as well. When we're thinking about what could be the dark matter is something that is massive, it's heavy enough to be slowly moving, it's weakly interacting, which means that it does not feel the strong force or the electromagnetic force, and it's neutral, so it's electromagnetically neutral. Of all the particles in the Standard Model, there are some particles that are characterized by those properties, namely what we call neutrinos. So we'll tell you in some detail why neutrinos are almost good enough to be dark matter particles, but not quite. So let's get along. Because the Standard Model is so complicated, we're going to start by giving away the punchline, telling you all the particles. Then we're going to back up and be a little bit more systematic, saying why we believe all those different particles are there. This is a picture of all of the fermions in the Standard Model of particle physics, all of the 12 different kinds of matter particles that make up what we find in particle experiments done all over the place. So, as you see, they come in patterns. There's a set of 3 families with 4 different fermions each. You have a pattern of 4 fermions, which is repeated 2 more times. The lightest family contains those 3 particles we've already talked about, the up and down quarks, and also the electron. But there's a 4th particle there. It's going to be called the neutrino. The neutrino and the electron together make up a doublet of fermions, a pair of fermions, fermions that are not quarks, by which we mean fermions that do not feel the strong nuclear force. So you have a nice kind of pattern in which there are 4 particles. 2 of them form a pair that do feel the strong nuclear force, and we call those quarks. 2 of them form a pair that don't feel the strong nuclear force, the electron and the neutrino. We call those leptons. That kind of makes sense, and then it's repeated again and repeated again. That doesn't make sense. At this point in our knowledge of the universe, it's a complete mystery to us why there are 3 families, or sometimes called generations, of elementary fermions. Then you have the bosons of the Standard Model of particle physics. There are 5 different types. We've told you about 2 already. The first is the photon. That's the most obvious particle in the world. It carries the electric and the magnetic force, responsible for all of chemistry through the exchange of these photons between different kinds of atoms. Then you have the gluons. It will turn out that there are actually 8 different kinds of gluons that carry the strong nuclear force. By the fact that there is something called the strong nuclear force, you will probably have guessed that there is also something called the weak nuclear force. The weak nuclear force is carried by 3 different bosons: the W boson, which comes in a positively charged type and a negatively charged type, and the Z boson, a single thing that is neutral. So the W plus, the W minus, and the Z are the three bosons that make up the weak nuclear force. Then, of course, you have the graviton. The graviton is the particle that carries gravity. Gravity is the most obvious force there is, but the graviton is hard to find. Because gravity is so weak, we have a difficult time decomposing the gravitational field into its individual particles. But the basic tenets of quantum mechanics say that it should be there, so most of us believe there is something called the graviton. You may have heard that there are four forces of nature, and those are them. The electromagnetic force with the photon, the strong nuclear force with the gluons, the weak nuclear force with the W and Z bosons, and the gravitational force with the graviton. The fifth kind of boson on the chart is called the Higgs boson. The Higgs boson does give rise to a force, just like the other ones do, but it is a little bit different. It has no spin, unlike the other particles, and most importantly, it has not yet been discovered. So we think that there are 5 forces of nature in the standard model of particle physics, but we've only found 4 of them yet. So that's the general picture. Now let's back up a bit and ask, how do we know? How do we get to the point where we believe in all these different kinds of particles? So the neutrino, in particular, doesn't feel the electromagnetic force or the strong nuclear force. When you say a particle doesn't feel the electromagnetic force, what you're saying is it's electrically neutral. It has no charge. The electron has charge -1, the up quark is +2/3, the down quark is -1/3, the neutrino is 0. So if the neutrino doesn't feel the electromagnetic force, and it doesn't feel the strong nuclear force, the question is, how do you find it? And of course, that's exactly the reason why it was the last of these 4 fermions to be discovered, because it is hard to find. It does, however, feel the weak nuclear force. It turns out that every fermion in the standard model feels the weak nuclear force, and that's how you find it. As a matter of experimental history, the way in which neutrinos were figured out is through the decay of the neutron. The neutron is a heavy particle made of 2 down quarks and 1 up quark, but it's unstable. The neutron left by itself will decay with a lifetime of about 10 minutes. The reason why neutrons exist in nature in such abundance is because when you stick them together with protons into an atomic nucleus, they can become stable. That's why some nuclei are stable and some are not, because you have to stick them together in exactly the right combination. But all by itself, a neutron sitting there will decay in a lifetime of about 10 minutes. And when people first observed these decays, they saw a proton coming out and an electron coming out. That kind of makes sense. The neutron is a little bit heavier than the proton plus the electron together. The neutron is electrically neutral. The proton has a positive charge, which exactly cancels the electron, so it makes sense that the neutron would decay into a combination of a proton and an electron. But when careful experiments were done, people measured the energy of the neutron ahead of time, and then they measured the energy of the proton and the electron that came out, and they didn't match. So when we're talking about the energy, we're of course including the mass of the particle. We have a neutron at rest, and it has an energy from E = mc². And then we add up the rest energy and the kinetic energy of the outgoing proton and electron, and you get a number that is slightly less than the energy of the neutron that you started with. So we're talking about early times in the 1920s, 1930s, when people were reinventing the laws of physics. Quantum mechanics had just burst on the scene. We were in the midst of a revolution that was getting rid of most of Newtonian mechanics, on the basis of which we had understood all of physics for the last several hundred years. So people were willing to believe that cherished notions were ready to be violated. So the first thing they did when they realized that the neutron was decaying into a proton and electron with less energy overall is they said, well, maybe energy is just not conserved. Conservation of energy was something they were willing to do away with to explain the decay of the neutron. But Wolfgang Pauli had a different idea. He said, what if energy is conserved, but the other amount of energy that we seem to be missing in this decay is coming out in an invisible particle? He invented an invisible particle, which then Enrico Fermi called the neutrino, which was Italian for little neutral one. The neutrino is sort of like the neutron, but much, much, much lighter. It doesn't feel the electromagnetic force. Now, in this day and age, we have a much more complicated theory of neutrinos, so I'm just going to tell you ahead of time that the correct description of the decay of the neutron is into a proton, an electron, and what we call an electron antineutrino. So the reason why it's called an electron antineutrino will become clear over the next lecture or two, but it's a neutrino-like particle. It turns out that Wolfgang Pauli was mad at himself for proposing the idea of the neutrino. He was actually kind of embarrassed because Pauli was an irascible old physicist who was famous for making fun of other physicists' bad ideas. And then he came along and suggested a particle that, as far as he knew, could never be detected. He thought of it as a kludge, as a mistake that we're trying to cover up something we didn't understand. But these days, we do know better. We know that there's an interaction that gives rise to that decay of the neutron into the proton, electron, and the electron antineutrino. And therefore, since there is an interaction that produces the neutrino, that neutrino must interact. And we're just much better at building detectors that are able to find very, very faintly interacting particles. So we have detectors that are able to discover neutrinos in large amounts. In fact, we're able to measure their properties. There's something called the Sudbury Neutrino Observatory in Canada that actually looks at neutrinos produced by the sun and looks at different types of neutrinos changing into each other. But on the basis of this kind of experiment, we're able to measure that neutrinos have a small non-zero mass. When Pauli first suggested the neutrino and Fermi developed the theory of it, they set the mass equal to 0. They figured that the energy it was taking away was all its kinetic energy. It turns out today we know there's a tiny bit of mass in the neutrino. You're still allowed to ask, though, why do neutrinos exist? On one hand, you can say, well, it hardly seems fair for there to be two quarks, the up quark and the down quark, and only one lepton, the electron. The neutrino completes a pattern. The up quark and the down quark belong together as strongly interacting particles that differ in electric charge by 1. The up quark has a plus 2/3 charge, the down quark has a minus 1/3 charge. Now, along with the neutrino, the electron is now a lepton that has a pair, and its other particle differs with the electron by 1 unit of charge. The electron has charge -1, and the neutrino has charge 0. So there's a pattern where you have two pairs of particles. It turns out that this structure is actually reminiscent. It's a remnant of an underlying symmetry that we don't see. In the deep down laws of physics, the electron and the neutrino are absolutely identical particles, and the up quark and the down quark are also absolutely identical particles. What turns out to be the case is that that symmetry relating these particles turns out to be broken. It's hidden from us, so it's a secret symmetry that is not obvious to us. You have to go either to very high energies or to very high IQ points to figure out that there's some symmetry underlying this. That's the reason we know that either the Higgs boson or something like it exists, because the role of the Higgs boson is to break that symmetry, and we'll talk about that a little bit more later. Still, even though the neutrino serves a purpose, the other fermions of the Standard Model, as far as we know, have no explanation. We have this nice structure where there are two quarks and two leptons. They fit together in a family. But then, in studies of cosmic rays coming from the sky, Carl Anderson discovered another particle called the muon. The muon looked exactly like the electron. It has the same kind of interactions, the same charge, -1 and so forth, but it was heavier. No one knew how to fit that particle into the structure of the particles they already knew. It didn't fit into this nice pattern of two quarks and two leptons. At the time, we didn't know about the quarks, but we had the proton and the neutron, and they formed a nice pair. And then people just kept finding new particles. So they filled in an entire new family. Along with the up quark and the down quark, we get the charmed quark and the strange quark. They are another pair of particles that form a doublet. Along with the muon, there is another kind of neutrino. So the old neutrino was rechristened the electron neutrino, and the new neutrino is called the muon neutrino. And then it happened again. Another pair of quarks, the top quark and the bottom quark, and another pair of leptons, something called the tau and the tau neutrino. So there are these three families in the Standard Model of particle physics. You can see some kind of pattern there. It sounds like there's some sort of symmetry going on, but nobody knows precisely what it is. The reason why there are three families of fermions in the Standard Model is still completely a mystery. And then, of course, we have the bosons of the Standard Model. Remember that bosons are force-carrying particles. Bosons are particles that can pile on top of each other. Fermions take up space, so you can't squeeze them too close together. Bosons can pile on top to make a big, noticeable classical field. So the electric field or the magnetic field are manifestations of many, many different photons piled on top of each other. Likewise, the gravitational field is a manifestation of many, many different gravitons piled on top of each other. So let's go through all of the bosons in the Standard Model, what we need to understand the forces that hold the particles together that we see. So there is one photon, of course. The photon carries the electromagnetic charge, but it is not itself charged. In other words, the electric charge of the photon is zero, so it doesn't feel the electromagnetic force itself. It carries the electromagnetic force between other charged particles. So the electron and other charged particles exchange photons, and that's the electromagnetic interaction. But the photon itself does not interact with other photons. That's just a true fact about photons. It's not a fundamental fact of nature. Other bosons do interact with themselves. For example, we have the gluons. The gluons are the particles that carry the strong nuclear force. They are self-interacting, so gluons can bump together and interact with themselves. But they're much more complicated in their interactions than photons can ever hope to be, and they're a little bit less natural and intuitive to us, so it's worth delving into the world of gluons to take a slightly closer look. The important fact about gluons and about quarks, about the particles that feel the strong nuclear force, is that they are confined. The strong nuclear force is so strong that we are not able to separate any two particles that feel the strong nuclear force. This is not just because we don't have access to quite enough energy to pull these particles apart. It is a matter of principle. You cannot pull apart two quarks far enough away so they look like elementary particles all by themselves. Quarks will always be bound together inside bigger particles, which we call hadrons. Hadrons are collections of particles that feel the strong nuclear force. So why is it that quarks are bound together inside strongly interacting particles? The reason is that unlike the electric or the gravitational force that grow weaker and weaker as you go far away, the strong nuclear force grows stronger as you pull things apart. As they're close together, they don't feel that much force and they just zoom around, but if they try to separate, the force becomes stronger and pulls them back together. So pulling apart two strongly interacting particles like quarks is like stretching a rubber band, trying to get a rubber band with two ends and to break off those ends so you only have one end over here and one end over there. You can't break a rubber band with two ends to make two separate ends that are not connected to each other, because what happens is the rubber band snaps and you get two more ends. Every time you have a piece of rubber band, there are always going to be two ends. You're not going to find one with just one end on it. That's how the strong interactions work. If you pull apart two quarks, what will happen is you will make a new quark-antiquark pair in between, and they will snap off, and you will get two more bound systems of quarks. You will never see a free quark or gluon all by itself because the quarks and gluons are so strongly interacting. In fact, as a little preview, this idea that when you pull things apart, they snap like rubber bands is the origin of the idea that instead of little particles, what we're dealing with here are little loops of string. If you chase that idea to its logical consequences, you end up inventing something called string theory. It turns out not to be a good theory of the strong interactions, but it is a good theory of gravity, as we'll talk about later. Okay, so that's the important feature of quarks and gluons. They're confined. Let's think about into what kinds of particles they become confined. When people looked at all of the different strongly interacting particles they could find, all of the different hadrons they could find, they noticed one important fact. They always came in one of two varieties. Either they were made of three quarks, or they were made of one quark and one antiquark. You never found a collection that was made of only two quarks. You never found a collection that was made of two quarks and one antiquark. It was always either three quarks or one quark, one antiquark. Or, of course, three antiquarks would be just as good. So they gave names to these particles. If a particle was made of three quarks, they called it a baryon. So protons and neutrons are the classic examples. They're both made of three quarks each. Protons and neutrons are both baryons. If something was made of one quark and one antiquark, they called it a meson. The pion, the things that carries the force between protons and neutrons inside the atomic nucleus, is a classic example of a meson. So people started to wonder, why is it the case that it's only these two kinds of configurations of quarks that we find in nature? Why is it that we only find 3 quarks, or 1 quark and 1 antiquark? The answer is that you can assign to quarks a quality called the color of the quark. And since they come in 3 kinds, the quarks are going to be either red, green, or blue. Those are the 3 colors that you can have. It is those colors that act in the strong interacting world like electric charge acts in the world of electricity and magnetism. The color of a quark is the source of its gluons, just like the electric charge of the electron is the source of its interaction with photons. So the reason why it's very clever to assign colors to quarks is because then you explain why you only get 3 quarks or 1 quark and 1 antiquark as saying that you only ever see colorless combinations of quarks as free particles. If you think about it from what you know about how your TV works, if you have red, green, and blue shining, they appear to you as white light. You can combine red, green, and blue together to make white. You could also combine red and anti-red together to make a colorless combination. If you like, you can think of red as cyan, anti-red as cyan, anti-green as magenta, and anti-blue as yellow. But most physicists forget that, and they just call them anti-red, anti-green, and anti-blue. So a quark and an antiquark make a colorless combination, a red and an anti-red, or a green and an anti-green. That's why you get only these 2 kinds of visible particles made out of quarks and gluons. You must combine quarks and gluons together into combinations that have no net color. Those combinations are either baryons or mesons. Gluons, sadly, are funny. They're a little bit difficult to explain. Every gluon carries simultaneously a color and an anticolor. So you'll have a gluon that is labeled as green anti-red, or a gluon that is labeled blue anti-blue, and so forth. So if you count in your head how many different kinds of gluons, there should be 9. There should be red anti-red, red anti-green, etc., 3 colors and 3 anticolors. But one of them is missing. There turn out to only be 8 gluons in nature, and this is the one time in these lectures where I'll have to say, you'll just have to trust me on this one. There are complicated mathematical reasons why that 9th gluon isn't there. There's one combination of those 9 kinds of gluons that doesn't exist in the real strong interactions. But roughly speaking, you can get pretty far thinking of the gluons that exist as combinations of color and anticolor. So if you're going to join them together, you're going to still have to stick to that rule that we only see colorless combinations. So now, those are the bosons we know, the photon and the gluons. There's 8 of the gluons. What about the weak nuclear force? I mentioned that the weak nuclear force is carried by W bosons and Z bosons. The Z is all by itself as a neutral particle. It's kind of like the photon, but it has a huge mass. The photon has 0 mass, it's massless, moves at the speed of light. The Z boson is also electrically neutral, all by itself, but very, very heavy. The W bosons are also very, very heavy, and there are 2 of them. There's one positively charged W and one negatively charged W. Together, these 3 kinds of particles carry the weak nuclear force. In fact, that's the reason why the weak nuclear force is weak, is because the W and Z bosons are very, very heavy. If you think of forces as being manifestations of bosons traveling back and forth, photons and gravitons, which are massless, travel back and forth very easily. Gluons are also massless. They travel only a short range, but they still travel back and forth very easily. Therefore, all of these things can stretch over distances and be very strong. Weak bosons, the W's and the Z's, are very massive, so it's hard to get them to travel from one particle to another. That's the reason why the weak nuclear force just doesn't seem very strong. It takes a lot of oomph to make a W or Z boson. In particular, let's think of an example of the weak nuclear force at work, and there is one classic example, the decay of the neutron. One of the reasons why the neutron lasts for so long is because the interaction that helps it decay is the weak interaction, which happens very infrequently. Neutrons last about 10 minutes, which might not seem long to you or me, but to an elementary particle that is incredibly long. All of these other particles of the Standard Model, which seem to be unstable to us, like the top quark or the charmed quark, decay away very quickly. The neutron lasts relatively long, and the reason why is because that decay of a neutron into a proton, an electron, and an antineutrino is actually a manifestation of the weak interaction. So we showed you a little picture of the decay of the neutron into an electron, proton, and an antineutrino. But here is a magnified view of that picture. What is really going on is that one of the quarks inside the neutron emits a negatively charged W boson, and in the process converts from being a down quark into being an up quark. In other words, the neutron, which was 2 downs and 1 up, becomes a proton, 2 ups and 1 down. The W that gets spit off then decays into an electron and a neutrino. So we have a better understanding of what happens when that neutron is decaying. It's really first emitting a W boson, and then that W boson is decaying. This is very paradigmatic of how modern particle physics works. We take an interaction that we see, it makes sense to us, but to understand it better, we zoom in on it with a microscope, and we see other more complicated interactions going on inside. So, those are the bosons that carry the weak nuclear force, the W+, the W-, and the Z boson. There's also, of course, the graviton. The graviton we've mentioned already. It is the particle that carries the gravitational force. The gravitational force is very obvious to us. It's the thing that keeps us here on the ground. We ordinarily think of it as either, if we're Isaac Newton, some force traveling between massive bodies, or if we're Albert Einstein, some manifestation of the curvature of space-time. But if we're good quantum mechanics, we think of it as the exchange between us and the Earth of a whole huge number of gravitons. We're all certain that there exist such things as gravitons. They're just the quantum mechanical version of gravitational waves. But each individual graviton interacts so very rarely that it's almost impossible to detect it. So, in fact, there's no plans in the immediate future, or what we should call the foreseeable future, to build a detector that would be sensitive to individual gravitons, even though we're sure that they're there. Finally, we have the Higgs boson. The Higgs boson is a little bit different than the other bosons. The photon, the gluons, and the weak bosons all had the same amount of spin, the same amount of intrinsic angular momentum. The graviton spins twice as fast as any of those bosons, but still the same basic kind of idea. The Higgs doesn't spin at all. It is an absolutely spinless boson. And of course, it's purely hypothetical. We haven't detected it yet. So sometimes you'll catch me talking as if we know what the Higgs boson is like. What we really have is a really good theory that predicts its properties, but we're still trying to test that theory. We're very hopeful that the Large Hadron Collider, currently being built at CERN outside Geneva, is going to find the Higgs boson explicitly, and then we'll be telling you about the measured properties of the Higgs bosons rather than their hypothetical properties. Why do we think there is a Higgs boson there? Because of that story I told you earlier about the secret symmetry of the Standard Model. The secret symmetry between leptons, between the electrons and their neutrinos, etc., and between the quarks, between the up and the down quark, etc. We can understand all of the interactions of the particles in the Standard Model if we promote the rough similarity between electrons and neutrinos and between up and down quarks into an absolutely true symmetry of nature. To do that, we have to explain why we don't see that symmetry. Why does the electron look like it has a different electric charge than the neutrino does? The answer is because there is some particle, some field, that exists and has a non-zero value even in empty space. We call that field the Higgs field. It's almost like it is filling empty space with a kind of molasses, through which these particles that would want to move at the speed of light are slowed down because they're moving through this medium. The particles we have in mind are the W and Z bosons, as well as every single fermion in the Standard Model. All of these particles have mass. If it weren't for the Higgs boson, they would all be massless. In yet other words, the understanding, according to modern particle physics, of the origin of mass of all of the fermions and the W and Z bosons in the Standard Model is a hypothetical field called the Higgs field, which we haven't detected yet. But you can get an idea why we're so very interested in detecting the boson associated with this field. It plays an incredibly important role in our understanding of particle physics. So that's it. That is the Standard Model of particle physics. We have 12 different kinds of fermions. We have 5 different kinds of bosons. So by now we can recall our mission throughout this whole project, which is to try to understand what is the dark matter of the universe and what is the dark energy. Dark energy we don't think is made of particles. It is a smoothly distributed energy density, about the same amount in space and in time, and we'll get to it in great detail. But dark matter is made of particles. Could it be any of the particles we listed in the Standard Model? The answer is no. The thing that we need to have to make a dark matter particle is something that has a mass, but is neutral and is stable. The only stable neutral particles in the Standard Model are the neutrinos. And for a long time, people were hopeful that we could understand dark matter as neutrinos. But the fact is, even though they do have a mass, that mass is too small to be the dark matter. It's not so small that you can't get enough energy density to be the dark matter, but if you do, you have particles that are very, very light moving close to the speed of light. That's not what you want in a good dark matter particle. If the neutrinos were the dark matter, they wouldn't form galaxies. They wouldn't form clusters of galaxies. They would come together as if they were going to form clusters or galaxies, but then they would just keep on going, close to the speed of light. You would not see in our universe the galaxies and large-scale structure that we know to be there if neutrinos were the dark matter. So that's bad news in the sense that we don't know what the dark matter is, but that's good news in the sense that 25% of the universe is something we haven't yet discovered. We will discover it as we look more closely, so in subsequent lectures we're going to go into details about what that dark matter might be.